The Subcommittee on Energy will come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. Welcome to today's hearing entitled Igniting America's Energy Future, the Promise and Progress of Fusion Power. I recognize myself for 5 minutes for an opening statement. Well, good morning, y'all. We've already had a chance to say good morning. We're glad y'all are here. Welcome to today's Energy Subcommittee hearing entitled Igniting America's Energy Future, the Promise and Progress of Fusion Power. After a decade of stagnation, most of y'all, I think the little young lady here was probably still in high school back then. After a decade of stagnation, U.S. energy demand is once again on the rise. This surge is driven by several factors, including the onshoring of supply chains crucial to our national security and the rapid growth of commercial artificial intelligence technologies across the country. At our last subcommittee hearing, witnesses discussed nuclear energy's potential role in powering AI data centers. That conversation led us to focus on nuclear fission, which is commercially viable today. This hearing will spotlight nuclear fusion, a field that after decades of promise has made remarkable progress across various technology readiness levels in recent years. These advancements have highlighted a growing need for workforce development. The challenge is not simply producing more PhDs, but building a robust, skilled trades workforce. According to the Fusion Industry Association, only 23% of employees in the sector are scientists and 44% are engineers, leaving a significant portion of the workforce without advanced degrees. The industry is expanding rapidly, growing by a staggering 50% in the last 2 years, while the supply chain has tripled in size in that same 2 years. Many fusion companies project operational pilot plants by 2035, with workforce needs expected to increase 6-fold at this stage, not including additional supply chain demand. To address these needs, our national labs are considering apprenticeship programs to help prevent potential worker shortages. Such programs would complement the cutting-edge research conducted at DOE facilities, which house much of the specialized equipment necessary for fusion science. Due to these unique capabilities, DOE's collaboration with the private sector is very vital for advancing commercialization. To foster these partnerships, DOE has launched several initiatives to connect, support, and indeed accelerate industry growth. These include a public-private partnership program, a milestone-based fusion development program, and ongoing funding for fusion projects through the ARPA-E office. Public-private partnerships leverage DOE's expertise while encouraging private sector investment. Milestone programs tie federal funding to demonstrated progress, and ARPA-E's early fusion projects have already generated over $700 million in private investment. These efforts are prime examples of responsible use of taxpayers' dollars. For decades, fusion energy was seen as a dream, always 20 or 30 years away. But recent successes at the National Ignition Facility, or NIF, have begun to change that perception. NIF became the first facility in the world to achieve a positive net energy output from a fusion reaction, as well as the first to achieve burning plasma. It's important to note that critical basic science questions still exist before we can see operational fusion power plants connected to the grid. Fortunately, academia, along with DOE user facilities, is working closely with the private sector to both identify and solve these remaining challenges. Continued federal investment is essential to ensuring these foundational science gaps are addressed in a very coordinated manner. The progress we've seen is undeniable, and the fusion industry is steadily advancing toward delivering fusion power to the grid. It can't get here quick enough, can it? I want to thank our witnesses for their testimony, and I look forward to today's discussion on how the federal government can support academia, the national labs, and private companies to ensure America leads in this critical race. Yield back the balance of my time. Recognize the ranking member.
Well, thank you very much, Chairman Weber, for convening today's important hearing on the current landscape of fusion energy, where we stand, what remains to be done, and how the federal government can play a pivotal role in ensuring U.S. leadership in a technology that could well revolutionize our entire energy sector. I also want to thank our very impressive panel of witnesses for being here this morning. The U.S. is at a critical moment in the effort to develop fusion as a carbon-neutral, sustainable source of energy. Breakthroughs in plasma physics, technology, public-private partnerships, and private sector innovation are giving us reasons to believe that fusion can become a game changer for clean power, climate resilience, energy security, and economic opportunity. In my home district, North Carolina State University has just launched a new remote control room under its Future Fusion Research Initiative. In July, the Fusion Plasma Auxiliaries Characterization Lab at NC State successfully conducted their experiment remotely at the D3D Fusion Facility in San Diego. This marks a significant step toward enabling greater student and institutional access to national and international fusion research facilities. It demonstrates how federal investment in infrastructure prepares students for the high-skilled jobs of tomorrow, fosters innovation and partnerships, and positions the U.S. to lead globally. Universities like NC State, our national laboratories, and private innovators depend on steady investments. Many of the witnesses here today will discuss how our nation's competitiveness in fusion is threatened by the absence of federal investments in major new facilities. Investments that would help address key gaps in materials science and technology development. Without that support, the U.S. will likely fall behind both scientifically and economically in yet another critical new industry. The federal role remains essential. Challenges like ensuring the stability of burning plasma, materials resilience, and reactor system design require substantial federal support. A trained workforce, and demonstration projects that can scale from experiments to net energy gain. These are the building blocks of a new clean energy future for all of us. I look forward to hearing from our witnesses about the current hurdles on the path to a U.S.-based commercial fusion industry and where federal action could make the greatest difference. I also ask for unanimous consent to permit Representative Don Beyer, co-chair of the Congressional Fusion Caucus, to attend this hearing and ask questions of the witnesses.
Without objection.
Thank you, Mr. Chairman, and I yield back.
Thank you, Ranking Member Ross. I now recognize the Chairman of the full committee, Dr. Babin.
Thank you very much, Mr. Chairman. This morning's hearing will examine the future of fusion energy and how the United States can maintain global leadership in fusion energy technologies. And I also want to thank our illustrious witnesses here. We're looking forward to hearing what you all have to say. But back to fusion has the potential to revolutionize electricity generation and reshape entire industries in our country. Beyond powering the grid, it holds significant promise for a variety of commercial applications, from providing medical radioisotopes for cancer treatment to enabling advanced materials processing techniques to propelling spacecraft in deep space missions. The private sector has emerged as a dynamic force in the commercial fusion energy landscape, with global investments now exceeding $10 billion, driven largely by American companies. This reflects a transition from government-led research and development to a market-driven, commercially viable fusion innovations that could transform energy production worldwide. Even major tech companies such as NVIDIA and Google are investing more in fusion power startups, viewing the technology as a promising way to meet their growing energy demands. Despite substantial private sector investments, the Department of Energy plays a vital role in making fusion become a reality. DOE's latest fusion energy strategy aims to accelerate the path to commercial fusion in collaboration with industry while coordinating fusion-related efforts across government, academia, and the public and private sectors. For example, at Oak Ridge National Laboratory, thank you for being here, is leveraging its deep expertise in fusion materials, plasma diagnostics, advanced modeling and simulation through 3 new research collaborations through the Innovation Network of Fusion Energy, or the INFUSE program. These partnerships focus on addressing practical engineering challenges essential to delivering fusion power to the grid by the 2040s. Additionally, DOE serves as the central hub for bridging the science and technology gaps that are necessary to achieve commercial fusion power. Its role is critical, as the federal government is the only entity capable of undertaking the high-risk, high-reward, long-term research and development required to address these challenges. And although significant progress has been made, much more work remains to fully harness the potential of fusion technologies. The rapid progress of the Chinese Communist Party, or CCP, in this sector poses a direct challenge to U.S. technological leadership. Historically, if the United States has led the way in fusion research. However, the CCP has effectively utilized its industrial base and civil-military integration to accelerate technological development and to rapidly scale critical infrastructure. It is also committed to connecting the first fusion-fission hybrid power plant to the electrical grid by 2030. The nation that successfully commercializes fusion first will likely set the global standards, the supply chains, and technological frameworks that will shape this industry for decades to come. Moreover, the implications go well beyond merely achieving technological leadership. They also raise important questions about global governance and our values. Fusion energy technologies must be developed and deployed by nations that uphold democratic values, transparency, and international cooperation, not by authoritarian regimes that might exploit energy dominance as a weapon. The U.S. must prioritize fusion energy development to outpace the CCP's aggressive timelines. Achieving leadership in fusion technology is not only essential for energy independence, but for ensuring that democratic values shape one of the most consequential breakthroughs of the entire century. I want to thank our witnesses again for their testimony today, and I look forward to a very productive discussion. And with that, I yield back the balance of my time, Mr. Chairman.
Thank you, Mr. Chairman. I now want to introduce our witnesses. Our first witness today is Dr. Stephanie Diem, Assistant Professor at the University of Wisconsin-Madison. Welcome. Our second witness is Dr. Will Regan, co-founder and president at Pacific Fusion. Welcome. Our third witness is Dr. Troy Carter. You know, we have a Troy Carter in Congress, right? No relation, I guess. I got you. Director of the Fusion Energy Division at Oak Ridge National Laboratory. Welcome. And our final witness is Dr. Bob Mumgard, co-founder and CEO at Commonwealth Fusion Systems. So we're glad you're here. Thank you. I now recognize Dr. Diem for 5 minutes.
Chairman Weber, Ranking Member Ross, and members of the committee, thank you for holding this important hearing and for inviting me to testify. My name is Stephanie Diem, and I am the principal investigator of a Department of Energy-funded fusion experiment and a professor at the University of Wisconsin-Madison. I also serve as the vice president of the University Fusion Association and was appointed as the U.S. Science Envoy with the Department of State. My remarks today reflect my own views. In a world facing urgent energy challenges and geopolitical tensions over access to energy and energy resources, Fusion gives us hope. Fusion is a dense, virtually limitless source of power derived from hydrogen that could radically transform humanity. Fusion, the process that powers the sun, occurs when light elements are forced together and combined under extreme conditions, releasing vast amounts of energy. On Earth, we use magnetic bottles or powerful lasers to create these fusion conditions. The resulting energy could provide large-scale baseload power and support applications such as hydrogen production, water desalination, process heat, and district heating. American innovation has long driven global progress in fusion. The United States is at a pivotal moment, marked by the achievement of controlled fusion energy at the National Ignition Facility in 2022, the continued emergence of transformative technological and manufacturing advances, and the establishment of public-private partnerships to develop fusion systems capable of generating electricity. But our leadership is at risk. Europe, Japan, and China are leveraging American innovation to advance their industries. History has shown us that when the U.S. invests boldly in research, it not only secures global leadership, but also delivers transformative benefits to society. We cannot afford to fall behind. Universities are the foundation of the fusion energy industry, powering the breakthroughs that will radically transform how humanity sources and depends on energy. I want to highlight 3 priorities for retaining U.S. leadership: continuing innovation to drive fusion science and technology forward, developing an agile workforce, and creating a robust fusion ecosystem. First, university innovation drives economic growth. The field of fusion energy emerged from publicly funded research, and universities remain the engines of innovation that seed new industries. Today, over 45 fusion startups are driving commercialization. 60% spun out of universities, and 95% of private investment has gone into those university spin-outs. At UW-Madison alone, federally funded research led to 3 fusion companies: Shine Technologies, Type 1 Energy, and Realta Fusion. Shine has already commercialized fusion by domestically providing critical life-saving medical isotopes, while Realta and Type 1 comprise a quarter of the DOE Milestone Program awardees who are designing first-of-a-kind fusion power plants. Together, they demonstrate how 20% of federal support can attract 80% of private investment, create high-skilled jobs, and fuel economic growth. Second, we need to build an agile workforce. Fusion energy is engineering at the extremes, requiring precision and advanced manufacturing. Federal funding has solved extraordinary challenges, but now we must scale those solutions into economically viable industry. The American fusion workforce faces personnel shortages, retention issues, education and training gaps, and limits in public engagement. To meet the demand, we must expand programs to include community colleges and launch apprenticeship programs. The recently introduced Fusion Workforce Act by Ranking Member Lofgren and Subcommittee Chair Obernolte lays out a coordinated response. Fusion can also renew America's industrial base, driving local and regional growth by revitalizing industries, creating jobs, and strengthening wages. Third, we need to grow a robust fusion ecosystem. Public-private partnerships like Infuse and DOE Milestone and FIRE collaboratives have laid strong foundations showing how universities, national labs, and companies can close these critical gaps together. To move swiftly from proving fusion science to developing commercial fusion energy, we need larger regional hubs supported by federal and state funds that coordinate efforts, maximize efficiencies. Universities will be indispensable partners in the coordination of these hubs by fostering innovation, interdisciplinary research that anticipates and meets the future technological and workforce needs of the fusion industry. Ongoing uncertainty in federal fusion investments poses serious risk. Funding delays strain universities that lack capital to bridge these gaps. These jeopardize workforce stability, research continuity, and pace of innovation while driving talent to other sectors or abroad, threatening the growth of private companies. Meanwhile, international collaborators and competitors are advancing with coordinated strategies, new infrastructure, and natural workforce initiatives, and major government support. Without a stable federal investment framework and coordinated effort, the U.S. risks ceding leadership in fusion energy. Continued public-private partnerships are essential to commercialization, and sustained federal funding will remain the catalyst that seeds innovation and drives the future of fusion energy. Thank you.
Man, you ended right on time. Boy, she's good, Dr. Regan. She speaks at about 400 words a minute with Gus up to about 650. So you got a row to hose. You're up next. Your testimony, please, sir.
All right. Thank you, Chairman Weber, Ranking Member Ross, also Chairman Babin, and Ranking Member Lofgren of the full committee, members of the subcommittee. Thank you for the opportunity to testify here today on the promise of fusion energy and for your longstanding support of the field that has finally brought commercial fusion power within reach. I'm Will Regan, President and co-founder of Pacific Fusion, As Dr. DM mentioned, fusion is what powers our sun. It's where you squeeze hydrogen into helium and release vast amounts of energy. The way we do it at Pacific Fusion is called pulsar-driven inertial fusion. We run a fast pulse of electricity across a tiny can of fuel, which squishes the can, squeezes the fuel, and makes it hot and makes it fuse. We can make power by doing this over and over, kind of like a piston engine. We're about 2 years old, have over 120 staff, and have raised over $900 million. We're on track to achieve net facility gain by 2030. So this is more fusion energy out than all of the energy we start with. This is something that no one has yet done. It's a critical milestone to get to power plants. And then we aim to generate net power by the mid-2030s. We're all here today because fusion could be the ultimate power source, creating a new multi-trillion-dollar energy sector and providing abundant power for industry and AI. What makes fusion so great? 3 things. First, fusion fuel is just extremely energy dense. You get millions of times more energy out per unit fuel than in chemical reactions. The little speck of fuel in our tiny fuel cans can power your home for a week. Fusion's compact. You can make lots of power on a little bit of land with a fairly small amount of materials, things like steel and cement. And fusion is safe. It stops when you stop driving it and makes no high-level waste. And the fusion industry, now on the cusp of commercialization, owes its existence to the visionary support provided by Congress. We founded our company in 2023 as a direct result of national lab breakthroughs in 2022. First, Lawrence Livermore's National Ignition Facility used lasers to drive controlled fusion ignition for the first time in history, releasing more fusion energy out than the laser energy they used to drive that. Around the same time, Sandia's Z machine showed that electrical pulses offer a far more efficient path to achieve ignition, and that efficiency boost lets you take the next step beyond ignition and get net facility gain, net energy gain. Also, a team at Lawrence Livermore in that same year demonstrated a compact modular technology to make those electrical pulses, which opens up an exciting path to make commercial inertial fusion power. So those 3 things gave us a great foundation to build on. And because our system is highly modular, made from widely available materials, things like steel, cement, steel, aluminum, plastic, oil, and water, we see a path forward to rapidly scale up affordable fusion power in America. And what's even more exciting is we're not alone. Not just us, but multiple American fusion companies like Dr. Mumgaard's are poised to soon demonstrate fusion energy. The problem is that China's noticed, and they're investing heavily to own this industry. Just since 2023, China has put upwards of $10 to $13 billion into fusion, including over $2 billion into a state-owned champion supported by one of their large power plant builders, and they've been rapidly constructing 4 major research facilities. They're aiming for fusion power by 2031, if not sooner. This is an existential threat to American fusion leadership and energy dominance. Our industry and Congress need to work together to make sure that America wins. How do we win? We need to grow our workforce, not just fusion scientists, but mechanical and electrical engineers, technicians, welders, and many others. The Lofgren-Obernolte Fusion Workforce Bill is a great start. We also need to start scaling our supply chain now. And I'm thrilled to see the Fusion Advanced Manufacturing Parity Act that was introduced yesterday. So thank you very much, Representatives Tenney and Representative Beyer, for this bill. We also need continued regulatory progress and certainty, building on the momentum of the recent NRC decision and also Congress's ADVANCE Act. But most critically, and why I'm here, is America needs to build fusion power plants before China, with shovels in the ground as early as 2028. And fortunately, America has a great playbook for this. We've used public-private partnerships to reassert U.S. leadership in commercial space, just for one example. We can run that playbook again through an accountable, milestone-based fusion demonstration program to jumpstart construction of multiple U.S. fusion power plants. I don't ask for this just to benefit us, but because this is what is needed to move the whole U.S. fusion industry forward fast enough to win this race. Thank you again for your time, Chairman Weber, Ranking Member Ross, also Chairman Babin and Ranking Member Lofgren of the full committee, and members of the subcommittee. Look forward to your questions.
Thank you, Dr. Rick. Dr. Carter, you're up.
All right, good morning. Chairman Weber, Ranking Member Ross, members of the committee, I'll add my thanks for having this hearing. I'm glad to be here. I'm Troy Carter, Director of Fusion Energy Division at Oak Ridge National Laboratory. Before I was at Oak Ridge, I was a professor at UCLA for many years, where I led the Basic Plasma Science Facility and directed the Plasma Science and Technology Institute. I'm also a product of NC State. There you go. I'm a big fan of the Wolfpack. Degrees in physics and nuclear engineering from there. Last time I appeared before this committee was in 2021. That was after chairing the process that led to the PSAC long-range plan, Powering the Future of Fusion and Plasmas. Okay, let me start. First, say it clearly, the investment that's been made by the federal government in fusion research has paid off tremendously. Over the decades, support from Congress, this committee, thank you, has enabled the U.S. to make extraordinary progress. We've learned, as one example, learned how to heat and control plasmas, the superheated gases where fusion takes place, at conditions approaching those required for fusion power plants. Investments in facilities have been critical. So examples, G3D tokamak at General Atomics in San Diego, several devices at Princeton, TFTR and NSTX, NSTXU, Alcator CMOD at MIT. This was central to this progress, absolutely important. In addition, there's been investments by NNSA that have been spoken about already. So the National Ignition Facility, the Z machine at Sandia. While these were built for stockpile stewardship, the breakthroughs that have been made there have direct implications for fusion energy. International collaboration is vital, remains vital. So there's a number of examples there. U.S. scientists contributed to record results at the Joint European Torus in the UK, at the Wendelstein 7X Accelerator in Germany. U.S. partnership and involvement in ITER, we're learning to build industrial-scale fusion while strengthening the supply chain for fusion. Investments in fusion R&D have had broader impacts. So Chairman Babin already spoke to this. There's a lot of spin-off technologies. These include semiconductor manufacturing techniques using plasmas, extreme ultraviolet lithography. There's been advances in high-temperature superconducting magnets that are now reshaping energy technology. And developing tools for controlling, analyzing plasmas for fusion. Our community has driven innovations in artificial intelligence. So these methods are now being used in manufacturing, robotics, and even drug discovery. All right, so a lot has happened. The opportunity before us now is to amplify that return on investment significantly by fostering a U.S. fusion industry. Thanks to this progress, we have a number of U.S.-based fusion startups that have raised significant capital and targeting pilot plants on ambitious timelines. I'll call out these companies that spun out of the public program, universities and national labs. So national labs in the case of Dr. Regan's and MIT in the case of Dr. Rumgaard. So that investment has helped lead to this. But significantly, okay, I should say, the ambition for doing this on a short timeline reflects the urgency of energy needs as well as confidence in the scientific foundation that has been laid by the public program. However, we have significant challenges ahead, and they're shared by all these companies, and we need to address them. Without strong public-private partnerships, these companies will face unsustainable risk as they move forward. And the U.S. risks ceding leadership in this industry that it helped create. Okay, so partnership is essential. We need to pair the speed and the innovation of industry with the depth and specialized tools of the national labs and the universities. We need to make these partnerships easier. It's challenging sometimes to set up SPPs and CRADAs with the companies for national labs to really do the work we need to do. We need to improve these processes, come up with more flexible ways to partner, and this will not only benefit fusion, it will benefit other fields that were U.S. competitiveness in fields like AI, if we can get the national labs lined up with industry and moving faster. All right, so we know what we need to do to get there. We've done, we're excellent at planning in the U.S. We've launched a lot of planning studies. The FESAC long-range plan is one of them. The plan is there, alongside National Academy studies that have called for the goal of fusion pilot plant, industry-led. We're starting to make progress on this. I came here 4 years ago. I said, now's the time. We have a plan, and we need to act. That message I'm still going to deliver today, because we haven't acted yet. But we're starting. There are some programs that we founded. So you look at the Milestone program that's been mentioned, the Infuse Partnership program that's been mentioned, and new fire collaboratives that were just launched. And these unite labs, universities, and companies on shared challenges. This is very important. We need new facilities. Those are called out in the planning documents. To close the gaps to the pilot plan, we need new facilities. ITER will give us access to burning plasmas and experience in building at industrial scale. Fusion prototypic neutron source, we need that to develop and understand and qualify materials that can withstand the harsh neutron environment in a fusion device. The materials plasma exposure experiment, choked up because it's my facility, now being built at Oak Ridge. We'll study plasma material interactions and develop solutions for fusion exhaust. We need a blanket and fuel cycle facility to close the gaps to commercialization. And I'll end, because I see my time is up, by saying that we know these facilities are being built in China, right? We see them happening and more, okay? So we need to act quickly. One more message in If I have more time, I don't, I think I'm out. I'll just say we need to invest in the public sector because we need to continue to push innovation forward. We need workforce. I'll add my thanks on the bill and just close to say that the decisive moment is now. With deliberate action, supporting facilities, partnerships, and innovation, we can ensure the U.S. leads in turning fusion from scientific promise into commercial reality. Thank you.
Boy, you're a fast speaker too, Dr. Carter. I thought I could sit in here and listen to you all day, and there for a minute I thought I was going to have to. So, Dr. Mumgarde, you're recognized for 5 minutes.
Chairman Weber, Ranking Member Ross, members of the committee, thank you for the opportunity to address you here today. I'm the CEO and co-founder of Commonwealth Fusion Systems. It's the largest fusion company in the United States and one of the largest fusion organizations in the world, second or third to the Chinese national program and the UK national program. Since my last appearance here 4 years ago, the fusion landscape has continued to evolve. We see a surge of private investment, we see significant scientific milestones, and we in the United States face an increasing sharp competition from foreign rivals, particularly China. We are at a critical moment transitioning from science to demonstration and the threshold of commercialization. I want you to take away 3 things here, 3 things to know. First, a working fusion power plant is not a matter of if, it's a matter of when and where. NIF has shown it's possible. The window is now open. At CFS, we're assembling our proof of concept machine Spark. It's the largest next generation energy device in the United States. And in a couple years, it will show commercially relevant net energy from fusion reactions. You know, the entrepreneurs, they see this shift. In 2021, there were 23 fusion companies with about $2 billion. Now there's 53 with $10 billion. 85% of that is in the United States. And it's not just venture capital or billionaires. It's sovereign wealth funds, it's banks, it's energy companies, hyperscalers. These are blue chip companies. The markets have seen that this window is open. Other countries see the window is open. We have significant policy shifts from Germany, the UK, Japan, and most importantly, from China. The second thing to know is this is a very high stakes race. This is trillions of dollars. Fusion is a foundational tool to build an advanced society. It transfers energy from being about natural resources, consumption, who has it, how do you get it, to being about technology. What do you know? How do you innovate? How fast can you build? AI makes this even more important because AI needs the type of power that fusion can make, and fusion needs AI. It's a flywheel, and that's why you see AI companies investing in fusion. And the race to fusion, that's the race to abundance. It's a hopeful message. We can't wait. At CFS, we are simultaneously finishing Spark, while we're also designing ARC, a commercial fusion power plant that we will build in Richmond, Virginia. Now, the third thing to take away is the U.S. is not positioned to win. China is. The U.S.'s leadership is under threat because we haven't made the investments and we're not sufficiently organized. In China, we're witnessing a coordinated state-organized intention to win. With state-sponsored companies, with the build-outs of test stands at massive scale, with multiple shots on goal. Analysis released this week from the Special Competitive Studies Project, which I'm a part of, estimates that China has invested $6.5 billion in new fusion facilities since the NIF shot. That's 3 times more than what we have spent over the same period. The U.S. is nothing like this. We're at serious risk of falling behind unless it takes urgent action and soon. Our fusion program looks much like it did even 10 years ago. Its test stands are aging. Its infrastructure is old. It's focused on science. It's not focused on moving to commercialization. The GAO report recently said that there's only about 2% of DOE funding that's relevant to building a fusion industry. Okay, what do we do? So the Fusion Industry Association and the SCSP Fusion Commission and others are calling on the U.S. government to do a one-time $10 billion investment in fusion research and demonstration. That's the level that it would take to do this. So what would that do? First, you would fund the commercialization programs that are already stood up. We've talked here about the Milestone program. That program, it shares risks. The companies that have won it have real shots on goal. And they say they need about $2 billion to be able to see what those power plants would look like before they start to construct them. That's way more than what is currently going into that program, but it's also the level that is near the level that's authorized. And then we would need another program on that milestone framework that would actually go and build a few of these power plants. And that would be, not unreasonable. It's very consistent with what we've done in other advanced technologies, if you think about commercial space or fission. And if we spend that money now, we won't have to spend 10x of that money later to catch up. And so that would amplify a key American strength, which is the competitive entrepreneurial ecosystem. Second, we need to invest in commercially relevant R&D at national labs and universities. No company can do this alone. There's still science and technology to be done, and that's where the crown jewels really, really excel. But they need the material test stands. They need the programs that build the workforce. They need the mandate to go work on that. And this means shifting funding and adding funding. It means shifting priorities. And all the roadmaps exist. The planning has been done. China is doing it. We just need to do it here. That's going to take like $4 billion. Third, we got to prime the pump for the future. Once we have the first power plants selling electricity, we're not done. We need workforce, we need supply chain, and we need a government program that can actually support that. That means an applied program. We should start planning that today. So in closing, the moment is now, and thank you for having me testify. I'm happy to hear what the questions are.
Thank you, Dr. Mumgar. The chair now recognizes the ranking member for at least 5 minutes.
Well, thank you, Mr. Chairman, and my apologies for being late. I did want to thank you, Mr. Chairman and Ranking Member Ross, for this hearing. As we all know, fusion has been a major focus of this committee and myself for some time. And the National Ignition Facility at Lawrence, it's still the only machine in the world that's actually achieved fusion ignition, has now achieved it 9 times with a big new record output of 8.6 megajoules just in April. So I agree that the milestone-based public-private partnership is excellent. It's made a big difference. DOE finalized agreements with the first 8 awardees just last year. We've seen, as you've mentioned, an infusion of private sector investment in fusion, $3.5 billion in the last 15 months alone, most of that going to companies located in the United States. But as you point out, China is ahead of us, and I am very concerned that we are not making the investments necessary to be the winners in this. I am very much opposed to President Trump's budget overall, but I would like to say that when it comes to a specific request for fusion, it's moving in the right direction, and I'm glad for that. We introduced Chairman Obernolte, Mr. Byers, who's here today, Ms. Trahan, and myself, an amendment to the Rules Committee to basically support the President's budget. Unfortunately, for reasons I do not understand, that amendment that supported the President was not made in order. But I'm hoping that we will continue to work on a bipartisan basis to get to where we need to go. And I would like to mention that Chairman Obernolte joined me last month in introducing a bipartisan STEM education and skilled technical workforce for Fusion Act, because we need to get, like Wayne Gretzky said, you need to skate to where the hockey puck is going to be. So I will just close with this. If I may just turn to questions, Mr. Chairman. Dr. Mumgard, you talked about the need for a $10 billion investment in fusion research and the demonstration effort, and I think that case has been made for some time. We've just never fulfilled it. Actually, we had the roadmap, and China took the roadmap and actually funded it. So that would be helpful, and you've outlined how it would be used, but we're not going to catch up through the annual budget process alone. If we're able to do this $10 billion one-time investment, what is next to get us to where we need to be? I mean, maybe Dr. Carter and others have views on that as well.
Yeah, so I think the idea of a kick, like a single program that can set the change in the trajectory, And that isn't just about the change in trajectory of like annual budgets. It's actually about the change in trajectory of the mandate. And if we have a goal to have a fusion power plant be built in the United States, and we have a program that is sufficiently scaled to help propel that, not the whole cost, the cost share of it, what that will naturally do is mean that the programs that are already running, that are sort of going off and they're doing good work, but it's not directed, are naturally going to align to it. And we see that in other programs in other areas of science and technology at the transition to commercialization. So I don't think it's a $10 billion one-time program and then suddenly we need to be at $5 billion a year of appropriations. We actually have a good pot of money, but we do need to see that shift and the level of commitment that's consistent with the ambition and commitment done in the private sector, frankly, and in other countries.
Yeah. Dr. Carter, you look eager to.
Absolutely. No, I agree. The $10 billion injection would go a long way to setting us on the course, as Bob says, Dr. Mumgard, sorry. In terms of getting facilities together, public-private partnerships, we'll need alongside of that the R&D programs to exploit these. Those should be PPP. We should be working together on trying to de-risk and develop the technology. We'll need foundational programs. We need to continue to innovate.
Right.
We'll need workforce. We'll need to set up supply chains. There's all kinds of things that need to be done as part of that investment.
I'd just like to say that the reduction in grant funding in research generally has not been helpful in advancing our quest to be number one and to achieve fusion as an energy source, and we need to address that as well. With that, Mr. Chairman, Ranking Member, thank you for letting me pop ahead of others, and I yield back.
Gentlelady yields back. Chair now recognizes himself for a 5 minutes question. Dr. Diem, in your testimony, you mentioned that academic programs are struggling to meet workforce demand, which is resulting in shortages of technical staff and manufacturing expertise. I think we'd all agree on that. So suggestions from you, what immediate steps do you think Congress can take to strengthen those apprenticeship programs and technical training so that we can ensure the workforce is ready before large-scale deployment? What do we need to do?
Thank you so much for that question. So in my research group, about 40% of the staff is technical staff. And when we had to fill an open position, we couldn't do it. So we have to depend on us finding someone with similar skills and upskill them in our lab. So an infusion of funds would allow us to build partnerships with community colleges and national labs and other fusion facilities to provide hands-on training for this. So a lot of the work that we do is very custom made. We're working in vacuum environments with strict materials requirements. And then we also have tolerances that you have to meet. We're working in a high magnetic field. So these are very unique things, along with working with exotic materials. And so one example that you could look at is at Princeton Plasma Physics Laboratory. They actually started an apprenticeship program where the only requirements is you're 18, over the age of 18, high school or GED requirement. You take classes at a community college, and then you're full-time employed at the lab, so apprenticeship for 4 years, and then you gain all these skills that you need, and then it's a benefit for the whole fusion facility, or whole fusion field. So expanding those programs, building that into regional efforts like Wisconsin, that already has a large manufacturing base.
Thank you. You said in your opening remarks, your testimony, that we should include those community colleges. What are you experiencing? Is that happening?
So right now, I have what I have is private donations to reach out to start these seed foundation programs, but we need more people dedicated to actually carry out the work. So part of it is the infrastructure we have on hand, but also the money to get people to help with the upskilling. Okay.
Dr. Mumgard, I'm coming to you. In your testimony, you mentioned how several fusion energy stakeholders are calling on the U.S. government to make a one-time $10 billion investment in fusion research and commercial development. Have I got that right? Good. What areas do you think should be prioritized to ensure that such an investment would deliver a long-lasting competitive advantage for the United States? I know that's going to be a little tough because you don't know exactly what China's going to do, but what do you think?
Yeah. We need to set on a course to get the first generation of fusion power plants built. So that's a demonstration program to actually put steel in the ground on designs that we've reviewed and looked at and said they're likely to work. The milestone program is set up to do that, but when you look at the total bill that's going to be, the companies have raised $10 billion. So like the cost share there is billions of dollars. But that's not alone, because like those power plants, they're with technology we have today, like if you forced it today, they would be kind of not great. We have technology that's in the pipeline, that's at the labs and universities. These are things like new materials, blankets, fuel cycles, that a lot of good ideas, but no way to really advance them or test them, because we don't have the test stands and we don't have the mandate. And so directing money to build the test stands and set up those programs at places like Oak Ridge, places like Princeton, places like Pacific Northwest, that would be really, really important. It's part of the long-range plan. And that would naturally, people vote with their feet on where things are going, scientists do, and that would create that outlet that people are looking for.
Thank you. That follow-up for you, Dr. Carter. In your testimony, you highlighted the need for new facilities like the fusion prototypic neutron source, say that 10 times, and the material plasma exposure experiment impacts to de-risk the path to pilot plants. How would you see this $10 billion actually being distributed to those facilities?
Yeah, I mean, the $10 billion, the facilities that we're talking about is really 4 that we're targeting, that I mentioned. The new ones that we're spinning up, the test stands that Dr. Mumgard mentioned, they might be, depending on how you do it. I mean, we really like to have a blanket test stand that you can test in a nuclear space. You can actually generate tritium and do all the things you need to do to understand closing the fusion fuel cycle, which is a big hurdle to commercialization. To do that, it might be in the billion-dollar class, but I think we can find ways to do it in partnership with the private sector, as well as looking at out-of-the-box thinking and how to get this done that could bring it lower. But that's what you're talking about. So you're looking at $10 billion would go a long way to getting you to those facilities.
I'm close to out of time, but there are often conflicting timelines regarding fusion energy, which becomes commercially viable, with some projections going into the 2030s, while other extended in the future. And just think about this, and I'll come back to it. Given these different timelines, how soon, I know this is a guess, a little bit of guesswork here, y'all can all think about this, can we realistically achieve fusion energy? No pressure, just give me month and day. So I'm gonna yield back and recognize the ranking member for at least 5 minutes.
Thank you, Mr. Chairman. I think we all can agree that fusion is, in addition to an energy issue, is a national security issue. And energy security is national security. Recent analysis shows, as we've discussed, that China is moving fast, in fact, faster than we are. At the same time, we have allies, the UK, Germany, Japan, South Korea, and others, that bring world-class facilities and industrial strengths. This is a question for all of you, so if each of you wants to address it, I don't mind using all my time on it. Do you support a tech-agnostic, U.S.-led, trusted fusion partners initiative focused on commercialization, supply chain onshoring, so that we and our allies together can build first and keep Chinese tech and suppliers out of this critical ecosystem? And whoever wants to go first, raise your hand. Okay, Dr. Mumford.
In general, yes. So the fusion world in the future, fusion industry, will necessarily be global. The type of equipment you need to make is of high variety, and the designs will benefit from having a global market. And so it makes sense to have the U.S. and allies working together. We should also recognize, though, that a overly constricted program would be detrimental. We want to encourage ideas and competition as well. So, like, we don't want to end up in a situation that is we're all going to the exact same place the exact same way. But it does mean that we can leverage each other's strengths. And I think when you look at the Japanese, the UK, they have distinct strengths, and the US has distinct strengths. And working together on the areas where strength reinforces strength is definitely what we should be doing. How to carve in the China angle becomes a little bit difficult because there are some in the middle. If you think about some of the places in Europe and some of the places, say India, which side are they on?
Does anybody have anything to add to that? Dr. Reagan?
Yeah, thank you, Ranking Member Ross. You know, I totally agree. Energy security is national security, and we want to incentivize as much benefit to the U.S. as we can, and that includes not just making fusion power in the U.S., but making fusion hardware in the U.S. So I'm you know, very excited by anything that helps do that. And again, thank you to Representative Tenney and Beyer for pushing forward the Fusion Advanced Manufacturing Parity Act.
Great. Looks like Dr. Diem has something to add.
Yeah, I can just add pretty quickly. So as U.S. Science Envoy last year, I went with a U.S. delegation through Germany. And so we had a great opportunity to visit our allies and what they had and see on site what they're doing to advance fusion energy and how we can work together to not duplicate efforts, but amplify what we're doing to accelerate the path forward. So one example is like trading of codes or modeling tools and capabilities. They have fabulous public-private partnerships, which is large spaces with many labs next to each other to foster innovation across that. So looking at those kind of models. And in the UK, I'm working with my colleagues on how do we have companion efforts that support each other, looking at how do we advance heating of these plasmas. So those are kind of a couple of examples that helps both of us without duplicating efforts.
Okay. And then would there, if this is a good idea, what concrete steps in the next 12 to 24 months should the federal government take to emphasize this across DOE, the State Department, and the Department of Commerce? Any suggestions? Yeah.
The UK is the closest. So they have facilities that are for tritium and blanket breeding that are very significant, multi-$100 million facilities. We could get access to them, but it would require the U.S. government having the agreement, but also putting in some money to fund people to go do the work there, the same way that they're funding people to do work there, basically to compete for time. That's a concrete example of those facilities.
Maybe we can tell the president before he comes home. Does anybody else have any suggestions? Yes, Dr. Carter.
Well, just to amplify what Dr. Mumgard said, I mean, we have strong relationships with UK, Japan, and Germany and the like. We've been working for a long time, but we do need that mandate, that investment from the U.S. side and agreements to clarify how we're working together, how that's going to work. There's, you know, now we're getting into a space where IP is being generated. How do we share that? So that's going to require some high-level discussions and agreements to get into place, plus the funding. Yep.
Okay. Thank you, and I yield back. I only have 4 seconds.
Gentlelady yields back. The gentleman from Tennessee is now recognized for 5 minutes.
Thank you, Mr. Chairman. Appreciate your holding this committee hearing. To each of the 4 panelists, I know most of you all very well. Thank you so much. To our dear friends at ORNL, thank you for doing everything very well. As most of you know, I'm the Republican lead on the Fusion Caucus. My other day job is I'm the chairman of the Energy and Water Subcommittee of Appropriations, which funds all of the great work that our Department of Energy does, including fusion. I have some questions, and I open it up because I so appreciate the fact that we've got a great blend of academia and business, and I meet with so many great researchers, whether they're from ORNL or from Princeton, but the fact that there's been such a great infusion of capital into from the private sector. So there's a great balance out there between R&D and seeing all this great capital coming in and the promise of us getting there. So my question for you all is, with limited budgets, and we are going to continue to fund fusion, but with limited budgets and choices to make, where should our federal dollars in fusion investment be going? And I'm solicitous of all 4 of your comments.
Well, I'll lead off. I mean, as I've said earlier, and as you know, we have laid out this plan. We have a strategy on where we need to invest. I think that's been made clear in consensus documents. You know, as we push towards the goal of energy of a fusion power plant, there's clear things that we have not invested enough in that we need to put money into. The facilities I mentioned, the R&D programs to go with them. I'll end with that.
Thank you.
The program right now is not in line with the recommendations of the national academies, the Fusion Industry Association, the long-range planning of the FESAC, because we haven't funded the programs that are needed to do the applied use of harnessing fusion power. So the materials, the test stands, the fusion prototypical neutron source, the tritium, the blanket. That stuff is not seeing significant funding. We still have a program that's very much on operating plasma physics facilities that are very large, they're expensive, and some of them are a bit old. We can collaborate and get results from other nations on some of this. We need to shift towards that. That was laid out in the community-driven plan, that shift needed to happen. It's laid out in the long-range plan from FESAC. We just need to do the shift.
Thank you.
And to support that shift, universities are really critical in they're able to be agile and pivot pretty quickly to address needs not only currently that are being experienced by private companies, but anticipate the needs down the line. So one example was we were building my experiment, we were running it for a while, and we had a failure. And I could just go to the building across the street and find experts in magnet technology and interfacing and just tell them about my problem, and they were like, whoa, my expertise can help fusion? I didn't realize that. And so that can be a catalyst not only now, but down the line.
Thank you.
Thank you, Representative Fleischman. And, you know, I think we all agree we need to win this race for America. And part of that is sustaining the great science we have. That is why the U.S. is the world leader in fusion, is because of the great universities and national labs that have brought us to this point. I just wanted to reiterate something I said in my testimony, which is I think one of the biggest returns the government, return on investment the government could see is from a fusion demonstration program for a couple of reasons. One, to match the intensity of the reinvigorated Chinese effort, but also to send a strong signal to the market and bring more private money off the sidelines to invest in this industry. Thank you.
Thank you. I really appreciate all four of your comments. And if I may, just a suggestion, as my colleagues on the dais know, I chair 8 energy-related caucuses, including the Fusion Caucus, but the National Labs Caucus, which is tremendous, and now most recently the American Dominance in Energy Caucus. The best thing about the caucus format is it's bipartisan. We have Republicans and Democrats. Every once in a while, senators come on in and visit, academia. So I welcome you. All of our caucuses that I run are free. I welcome you to come on in and speak with us. I know Mr. Weber, Chairman Weber, and Chairman Beyer frequent our caucuses. They're convivial, but they're productive. So whenever we have these events, please check with us, and you're always welcome. With that, I yield back.
The gentleman yields back. The chair now recognizes the gentlelady from Oregon, Representative Salinas, for her at least 5 minutes.
Thank you, Mr. Chair, and thank you to our ranking member for the hearing, and thank you to our witnesses for being here. Dr. Diem, you mentioned the Great Lakes Fusion Energy Alliance and suggested there would be value, all of you have, in public-private regional hubs to expand the fusion ecosystem. This sounds a lot like the Hydrogen Hub and Direct Air Capture Hub programs created by the bipartisan infrastructure law. However, we also have the Department of Commerce Tech Hubs program created by the CHIPS and Science Act, where several tech hubs already focus on areas relevant to the fusion industry, from material science to advanced manufacturing, or in Oregon's case, semiconductors. Are you suggesting we need a dedicated regional fusion hub program of sorts, or is there potential to expand coordination with existing efforts like the regional tech hubs?
Thank you for your question. So, as I mentioned, fusion has really unique challenges that are different than the semiconductor industry. So these ultra-high vacuum environments, these exotic alloys and things like that. So I think a targeted effort that really focuses on that. And the reason why we've worked a lot in the Midwest, specifically in Wisconsin, is because we built so many experiments. We worked with a lot of small machine shops. And so we built through this relationship, they've understand our challenges, but to scale up to a large industry will take a coordinated, targeted effort to really understand the uniqueness of those. So I could see some cross-collaboration, but really a hyper-focus on the fusion aspects too.
Thank you, that's helpful. Would anyone else care to weigh in?
Sure. Well, I'll support what Dr. Diem said. I think these kind of regional hubs could serve many purposes for growing the ecosystem. We talked about these test stands that we need to grow. It might be a model in a regional hub where you have investment from the industry, from the government, from philanthropy, from all over the place to try to build up these hubs. You could follow the model of other consortia where you have companies buying in to get access to facilities, getting shared IP out of it. In addition, there's a workforce angle. So these hubs provide a focus point for drawing in. You want to coordinate the community colleges, the trade schools, and have them all be on the same page on what we're trying to do. And so that provides an opportunity to do that too. So I'm fully supportive of that idea.
On the idea of like how to blend fusion with other things, I think it's always important to start with the end in mind. A working fusion industry is a very large industry. And so that means in the future, we are likely to have things like academic departments that just do fusion, the same way that we have academic departments that do aerospace or that do fission. And so in that framework, like when's the first time we see a fusion hub? Because eventually we would have to have one.
Thank you. Dr. Regan, did you want to jump in?
Yeah, I'd like to just double down on Dr. Mumgard's point. I think something that we need to see more of is cross-disciplinary programs that bring together folks from many different disciplines: mechanical engineering, electrical, thermal, nuclear systems engineering. All these things have to come together to not just do the fusion science, but now build fusion power plants.
Thank you. So a few of you have mentioned this on the intellectual property side and cross-collaboration. As we get into this world, and I think I visited Helion a couple summers ago, this was a big concern, especially when it comes to protecting IP and China. Do any of you have suggestions for how we move ahead and how the U.S. can be a player for the industry in protecting that intellectual property and making sure that it doesn't fall into the hands of adversaries? To any of you? Sorry if this is a question you weren't anticipating. I'm sure my staff is like, where did that come from? It's not in my list of questions.
It's a very good question. The first thing is, IP is really only useful if you're able to make a large industrial return on it.
Right.
And so we can oftentimes get too hung up on the IP versus like what is the pull that's going to pull the industry into existence. And the easiest areas of IP are areas that everyone needs, because that means the companies themselves have a reason to share. Whether or not that falls into adversary hands, well, if we don't build something in the United States, it's not going to matter if the adversary has it or not. We have to actually do both.
Thank you. Does anyone else care to weigh in? Dr. Regan?
Yeah, I think this brings up another important topic too, which is the balance between what you publish and what you protect inside the company. So I think that's something that's come up a few times. I think it is important to publish and put out scientific work to stress test what your company is claiming against the thousands of brilliant researchers in the U.S. And it's also critically important to have a robust portfolio of patents and trade secrets. Just to add one more thing to what Dr. Mumgard said, another big advantage in addition to IP is know-how, the expertise, the talent base, and capabilities. So the kind of machines that our companies are building and that could be built at national labs do provide an edge that you need those to make progress. Thank you.
Thank you. I'm just about out of time. I yield back.
Gentlelady yields back. The chairman now recognizes the gentleman from Colorado for 5 minutes. No? Let's go with gentlelady from South Carolina for 5 minutes, at least 5 minutes.
Thank you, Mr. Chairman, and thank you for holding this hearing today on fusion energy. And I would also like to thank our witnesses for being here. The United States is at a critical point for our energy infrastructure. Our energy output has stagnated over the last 20 years, while the demand for energy is increasing rapidly across the board. Fusion energy, as part of an all-of-the-above solution, offers the United States a chance to maintain both energy and technological dominance, to keep rates low, and to build out our industry once more. From industry suppliers to university research partners, the 3rd District of South Carolina is proud to have a role to play in the future fusion energy landscape. Many of our constituents also work at the Savannah River National Lab, which has decades of expertise in working with tritium, an essential fuel for the nuclear fusion process. As fusion becomes a viable energy source, expertise in handling, processing, and using tritium will be vital in establishing a safe and secure process to expand our energy infrastructure. So I would like to open my question to the entire panel. What steps are the Fusion Energy Sciences program and the fusion industry taking to build a robust safety culture around operations with tritium in the construction and operation of fusion plant pilot plants?
This actually dovetails nicely with the IP question. So the industry has a pretty consensus view that in issues related to safety and public acceptance, we should be very open and collaborative with each other. So that means when we develop fuel cycles, when we have issues about safety cultures, we share. And so there's actually a tritium working group that the DOE convenes, it's international, that pulls in people from all the different users for tritium. And they share best practices. They tour each other's facilities. We actually just hosted them out in Devens at the Spark facility. And so that's an example. We have a strong culture already in this. The other thing is that when we site these facilities, these are new and novel facilities. And that means you have to go into communities with an education mindset and a listening mindset. That we can't go and put fusion facilities, black box facilities, in places that people don't know they're there or that they don't have consultation. The good news is that when we do go and say, hey, would you like this? Would you like to learn about it? We see broad engagement and we see favorable attitudes. So we've cited 2 facilities, one in Massachusetts and one in Virginia. And in both cases, we were surprised at the level of questions, very, very educated, and also the excitement about a new thing in their community. And they asked questions around safety and tritium, and we were able to turn them to people like at Savannah River.
So thank you so much for your question. So Savannah River National Lab has great experience, and they're also leading a fire collaborative that's focused on the fuel cycle. And I think it's really important because you're leveraging their historical, expertise in that. They're also engaging universities in that work as well. And I'm part of that fire collaborative. And part of what we do is around tritium byproduct material and also engaging the public in that. So that provides an important space in the safety aspect and also the siting and going out into communities as well.
Thank you.
Just quickly add, I think the national labs provide, especially Savannah River on tritium, provide a wealth of expertise, and I think that's essential to share that as we develop a stance on how we regulate and license fusion devices. So certainly Organization of Agreement States is leading the way on that, with Tennessee taking a lead. And I think making good use of the knowledge and expertise at Savannah River, at Oak Ridge, and other places is going to be essential to doing that. Right.
Thank you. My time's almost up, so I'll yield back.
Gentlelady yields back. The chair now recognizes the gentlelady from North Carolina for at least 5 minutes.
Thank you, Mr. Chair, and thank you to the witnesses for being here with us today. I'm proud to represent North Carolina's 4th District, home to 3 research universities, including North Carolina Central University, one of the 10 HBCUs in the state. Dr. Carter, what are the most impactful actions Congress and the federal government can take to strengthen and expand partnerships between our national laboratories and HBCUs to build the skilled workforce needed for the future maturation of fusion energy technology? One that comes to mind is Hampton University and their Starlight Fusion project, which demonstrates how direct investment in HBCU-led research can ignite broader participation and innovation in fusion science.
Thank you for that question. I think it's an excellent question. I'll say a few things. So first and foremost, Hampton, I'm going to visit there October 1st to tour the facilities and meet with Calvin Lowe, who I work with on fusion workforce activity, actually. So very glad to have connection and grow that connection with them. I think university partners of National Lab, to me, are absolutely essential. I mean, it's a partnership in getting at the innovation that the universities can provide. And what comes with it, I mean, first and foremost, the innovation. What comes with it is the students and the workforce, right? And so they come along, and that's a huge benefit to us. So how do we make this a stronger connection? So DOE has funded some activities under the Renew program, and Oak Ridge has led a couple of these that have been focused on getting regional universities, including HBCUs, involved in our programs. And so this has led to internships, a fusion energy boot camp that one of our Renew programs is starting, modeled after the nuclear boot camp that has worked well in that industry, to try to give students at those institutions, and importantly, the faculty. The way you maintain this relationship is not just picking up the students and bringing them in. You want to engage the faculty and have them be part of your programs, feel like they have a leadership role. So we need to have that happen with Calvin at Hampton and other institutions like that. Yeah.
Following up to that, can you share your experience with international students at the national labs and universities and the role they play in pushing fusion research forward in our country?
Yeah, I mean, we've always got the best and brightest to come to this country because of what this country represents and the opportunities. They want to be part of this program because they see what we're doing in fusion energy. So, my role at UCLA, my role now at Oak Ridge, international students have been key. They've come into our programs. They've made tremendous contributions. All the science that's been pushed forward, you can point to people coming from all over the world coming to the U.S. I'll point out to the students that have come through my program at UCLA, all of them have remained within the U.S. as they go on their career, and they've made tremendous contributions in doing that. At the national labs, look at my division now, we have amazing staff that come from all over the world that are there contributing their scientific talent, engineering talent to pushing forward fusion. It's essential. We need to embrace getting the best and the brightest here to make this work. That's been how the U.S. has gotten where it is now, and we need to keep doing that. Yeah.
Thank you for that. Dr. Mumgard or Dr. Regan, from a private sector perspective, how important is it that the United States has a sustainable international talent pipeline to pull into specified fields such as fusion research?
It's essential. Fusion is a global exercise. The fusion process is a universal thing. And so the investments made around the globe to create talent, that's what we thrive on. We pull people in from Japan, Korea, Germany, and we need to keep that pipeline going. We use the O1 visa for fusion expertise. And that, if you look at just the tech industry overall, that's been a backbone of the tech industry. And so fusion's no different in the sense that a smart single individual can make a society-level contribution at the birth of an industry, and they're essential.
Dr. Regan.
Yeah, thank you. I'll add to that a little bit. Yeah, I fully agree with what Dr. Mumgard and Dr. Carter said. I mean, we need the best and the brightest to come here, and specifically, we've talked about some of the capabilities that our allies have, like the UK and Canada are, they have Canada's where most of our tritium comes from. So it is essential to bring in that talented workforce, especially when there's international capabilities that we want to benefit from here in the U.S.
Thank you. That's my time, Mr. Chair. I yield back.
Gentlelady yields back. The gentleman from North Carolina is recognized for 5 minutes.
Thank you, Mr. Chairman, and thanks to our witnesses for your testimony today. I'll be honest, though, I found it a little bit distressing. And I just want to have a quick conversation with you. I want to gain some clarity on this. We have talked, several of you talked about, we're really falling behind China. And that's happening at a very rapid pace. And I really want to kind of understand why. I know Dr. Mumgard, you talked about how since 2022, China has spent $6.5 billion on investing in fusion research. And during that same period of time, the U.S. has barely done just over 30% of that investment. But I really kind of want to wrap my mind around what's happened here. Because if we're falling behind and we've made massive strategic investments, you all are here with your hands out for another $10 billion, right? Yet the testimony that I've heard today really can only be characterized as we're failing. And I'm genuinely not saying that as an attack on you. I'm saying that from the perspective of an American. This is a very bipartisan committee. The work that we do is critically important for the future of our market economy and our national security. But we've done something wrong here because we've invested $40 billion over the last several decades in fusion research, and we're behind. How did that happen? And is China stealing our research and development? Are they smarter than we are? Are their strategic investments better because they're doing a significant amount of investment in a very short period of time when we are basically running a slow burn of investments across a long period of time? And I say this only from the perspective of I hate losing, and I'm not willing to let this country lose to China in this space. How do we fix it?
Thank you for the question. I also hate losing. What they've done is they've done the same playbook they did in other areas. So they're not a leader in innovation. We are a long-term investment leader in innovation. But when the time comes to put something at risk at scale, they have the ability to mobilize to do that in a way that the U.S. doesn't. They have a centralized control system that allows them to pool large amounts of money, capital, and organizations to go and build things that need to be built. And fusion needs things built. And so the fusion advances don't happen just in labs of single PIs of bright people that come here. They happen in coordinated fashion by building multi-billion-dollar facilities. And the Chinese have seen that those facilities will pay off. They saw NIF. And they immediately said, let's build one that's a little bit bigger. It's not as advanced. It's probably a generation behind in technology, but we'll make up for it in speed, scale, and coordination. And like the reports are that there's people working 24 hours a day on building that. There's students on cots because that's the playbook, hard and fast the minute the window opens. We sort of are still debating whether the window is open, and that's to our detriment.
Yeah, just to follow up on what Dr. Momgard said. I mean, I think the investment that's been made, there's been tremendous payoff. I mean, the U.S. has innovated and got us to the point where we are. The world, you know, China is building things that were designed and developed and ideated in the U.S., right? So the moment that we have before us is to actually carry it forward. So we've set the ground, we set the stage, we set the ball, right? We just need to spike it, and that's where we are. It's not that we failed. If we don't take action now, we will. So now's the time to move forward, and we have to change our approach and our mindset. We're trying to get to a commercialized energy source. We got a lot of R&D to do, but we have to change the way we're approaching it.
Just a few comments too. You know, I agree. You know, we can't afford to lose this, and we wouldn't have started our company if we didn't think we could win this. Our company could win this, and America could win this. I want to reassure you. I think we still do have the lead, but now is the time to act on that lead. And I point to programs that NASA COTS program has come up as a great example. Like that is a great example where we were the ones that developed the technology. We got to space. We lost that industry to Russia, but then the NASA COTS program came in, and with a catalytic investment of, you know, that was around $800 million, that reasserted U.S. leadership. We now own that commercial space industry again, and that investment is worth, you know, 500, 1,000x what the government put in that for an American industry.
People really drive innovation here. And we see it time and time again. And universities spin that, right? And we also provide workforce. But if we start contracting those governments, federal investments in those sectors, we lose people. Right now, we're at risk of people leaving for other sectors I mentioned, but also other countries. The day my grant ended this year in a federal uncertainty level of funding, I actually coincidentally received a foreign talent recruitment email. And so when you're in stress of like how I'm going to fund these early career researchers to keep this innovation drive that will then, impact private industry, that's really scary, right? And so you're looking at how you can keep supporting that innovation. So I think making that that certainty continue with federal funds is critically important.
Thank you for your responses, and I appreciate the commentary. The only thing I tell you is outcomes matter. They're everything. We've got to win. Thank you, Chairman.
Gentleman yields back. The chair now recognizes Dr. Foster for 5 minutes.
Thank you, Mr. Chairman, and to our witnesses. I guess I'll start with Dr. Mumgard. You know, the question was coming. What's the status of your testing of production coils, and how many of them have survived a full energy quench and so on?
Yeah, so we use a machine called a tokamak. It's basically a magnetic
I understand
bottle.
the machine very well. Okay, I'm old friends. I'm high school friends with Mike Zarnsdorf, who's known to many of you.
We've produced about 95% of all the required magnet pancakes.
How many of them have survived a full energy quench?
We've quenched one, and it has survived, and we did it intentionally. Full energy, full quench.
Full energy, the full magnetic energy.
Full magnetic
Of
energy.
the full system. So this was running above nominal current.
You have to adjust for it's a single coil, but yeah, it's not quite full energy. It was like maybe you have to do a geometry adjustment, but very, very significant. And with the quench protection system working, the same one that we had developed after the previous coil, which we intentionally quenched and intentionally destroyed to learn how it worked.
Yeah, okay, and so could you briefly say, what is the quench detection and prevention and quench spreading mechanism?
Yeah, it's a series of heaters.
Okay, so this
it's
is
very similar to what CERN uses to take down their.
Well, it's what we invented at Fermilab to make our magnets
very
survive many years ago. Okay, so this is good. I've been telling you for like a decade you're going to need a very serious quench spreading system, and I'm glad that,
it works.
It's worked once. Your lifetime.
Yeah.
You got to cycle this. I don't know, 30 times or something. I don't know what your the lifetime number of quenches. All right. Anyway, it's good to see that you're doing testing, but it's really, really important. You've raised a lot of money, and if you have a problem with magnets, we've seen in high energy physics, large accelerator projects canceled because they built everything, but the magnet didn't work. So keep your eyes focused on the magnets, and I'll continue asking that question. The other thing is the energy density on the diverter. Do you have a design that actually, at least on paper, might work?
Yeah, that's a good one. So actually we do. It's called an advanced diverter. And interestingly, the TCV tokamak, in a collaboration, recently showed the experimental results that look really, really promising, that actually spreads the heat out. And that validates modeling done at Oak Ridge and a couple other places that show that by basically magnetically extending the region of the plasma interaction, you can get a pretty good light bulb.
Okay, all right. So I look forward to see that being published and the whole simulation known. Let's see, Mr. Regan, do you have a parameter set for something that would actually make energy economically? I mean, what is the cost per target, the cost per pulse, the efficiency, just a high-level parameter? Is that how much energy, fusion energy do you expect per target?
Yeah, thank you for the question. So the scale of so right now we're building what's called the demonstration system. That's intended to get net facility gain. That stores about 80 megajoules to produce 100 plus megajoules of output. In a commercial version of that, where we're cycling it not once a day, but once every few seconds, we're aiming for facility level gains of say like 5 or 6. So you're storing, say, in this case, maybe it's 100. You're getting 500 to 600 megajoules of output.
All right, and so do you have a published parameter set that says okay, you have okay?
I'd refer you to we published a paper called AMPS. It's affordable, manageable, practical, scalable. It was a set of criteria and a technical roadmap. We put it on the archive in April, and it's published in Physics of Plasmas earlier this month.
Okay, and so then the big difference between what's been proposed with normal Z-pinch devices is that you have a more efficient drive mechanism, which is basically, I think of it as an induction Linac with a beam shorted with a piece of copper for a tapered impedance line. Is that pretty much what it is?
It's we use a technology called an impedance match Marx generator. So it's an evolution of the old school Marx generator that gets pulse compressed on facilities like Z.
But it's got induction. It's got a bunch of ferrite or something equivalent in it.
Oh no ferrite. Actually, so the IMG is an improvement on the linear transformer driver, which is a Russian technology. So we improved and simplified a Russian technology to make the IMG, or the national labs did.
Okay.
And now we're building on that.
All right. And do you have worries about the lifetime of the switch, whatever you're using?
Yeah. So the switch and the capacitor are the two components we have to have long lifetimes for, and we're working on that. Yeah. So with our demonstration system, we only need a few thousand, tens of thousands of shots. the switches we make today are plenty capable of that. And there are known pathways to extend those lifetimes to a rep-rated power plant.
Good to see you're working on the
Oh, yeah.
important problems, okay.
Oh, no, this is very important to us at the very start of the company to make sure that we have a practical path forward to make a power plant that lasts for decades.
Okay, and let's see if, Chairman, can I have another 15 seconds, 20?
If you'll do it in English.
Okay, all right. All right, sorry. All right, Ms. Diem, you should add to your list of spinouts from University of Wisconsin Plasma Physics a company called Electronic Theater Controls. 50 years ago, I was working in the plasma physics lab there as a young student, and on the evenings after we'd completed our work, I kind of took advantage of a lot of that equipment to build our prototype. I took advantage to computers at Oak Ridge, the PDP-10 that we could get access through that lab, and that was, we didn't have a CRADA, but we had a very strong set of we made a lot of use of the technical resources of the Plasma Physics Lab on an informal basis, and that was necessary to get our company going. And that company now, it's $450 million a year, 1,500 employees, fully owned by the employees who owned it out in Middleton, Wisconsin. So claim credit for that one, too.
Thank you, I will.
The gentleman yields back. The chair now recognizes the gentleman from Indiana, Dr. Baird, for his 5 minutes.
Thank you, Mr. Chairman and Ranking Member, and I always appreciate all of you witnesses taking the time to share with this committee and us your insights into whatever the program is that we're discussing. But you know, the thing that's of interest to me, I think there's a lot of sentiment to see that all sources of energy are available or on the table. We've got fossil fuels, we've got nuclear, we've got solar and wind, and there's been some concerns about that. And now we're talking about fusion. And Dr. Regan, you mentioned the return on investment. So I guess here's my question. You know, Secretary Wright recently said that fusion energy was a source of limitless, reliable, American-made energy. And I think we want to take back that lead in the energy production. So can you explain why this fusion energy is important as a potential future energy source, and what role you envision fusion energy can play in the future mix, and how fusion can contribute to the concept of energy abundance and energy security. I guess what I'm really trying to get at, if we're going to invest in that, and I know it takes investment sometimes to get things moving, and I really appreciate what the national labs do. I really appreciate what the private industry does, and I really appreciate what the land-grant universities do. So I guess I guess my question is, tell me why I should invest in fusion energy and that kind of research. Am I going to get a return on my, and that's to everyone.
Thank you, Representative Baird. Yeah, we fully agree. You know, we need all of the above. Energy is prosperity. We want more of it. More is better. And just, you know, as has been discussed earlier, energy is a critical factor in the AI race. So I see what fusion offers is a new and, you know, revolutionary source of energy that, you know, it can be low cost. The fuel will last us forever. And I think, yeah, that's an important capability. And like Dr. Mumgard said, it's not a question of if it's going to happen, but it's going to be when and where. And we want that to be in America as soon as possible.
You know, energy is prosperity. Like, we built this country on energy. You cannot have a rich country without energy. But of course, energy comes historically with externalities, right? There's a lot of people involved that are around an energy facility, and if the energy facility is very spread out, there's a lot of people involved in that. And of course, if the energy facility consumes or emits things, there's a lot of people that are affected by that. What fusion does is it gives you energy with very small externalities. So that means it's like not just energy sovereignty for the nation, it's energy sovereignty for the community. It puts things into a plant that you build this plant, you put the parts there, and you have energy. You don't have pipelines coming in that can be shut off, and you don't have smokestacks of stuff coming out that can go places. And so that's a different paradigm. It takes a bunch of trade-offs out of the energy equation of like who's giving up something for someone to have energy. And you know, conceptually, it's a facility that you build like you build a power plant today that hooks to the grid like you build the grid today, that has operators that are like the people that are there today, that has fabricators that are like the people there today. And so it's a continuation. It's not a disruption of the energy system in terms of delivery. And those make it very, very, very attractive.
And I think it's an important part of a broader portfolio because a lot of different communities can rely on other different forms of energy. But what it brings you is this energy density that's just unfathomable. So it's you get 1 million times more energy out when you burn when you burn oil. So as an example, your whole entire lifetime, if you want to power it by coal, you have to burn 280 tons of coal. The equivalent fuel would just be you take heavy hydrogen out of 2 bathtubs full of water and 6 laptop batteries. I mean, that could transform everything as far as how we power and how we enter the next phase of humanity.
Anyone else? You know, the other thing that's interesting to me is our the people in my district, we're talking about a significant increase in the need for energy because of these data centers. And so I guess I was kind of interested in how that might fit, how fusion might fit in that ballgame. So, but anyway, my time's about up, and I really appreciate you being here. Thank you. I yield back.
Gentleman yields back. Chairman, I recognize the gentleman from Arkansas for 5 minutes.
Alaska.
Alaska, Arkansas, for Texas, they're all the same.
It is not the same. I'm 2.5 times the size of Texas.
I'm sorry, the gentleman's time has expired.
Okay, start the clock. All right. So we talked a lot about the sort of egalitarian motives of fusion power, and I'm a big supporter of fusion power. You know, we talk about what a gift this would be to humanity, really. But we're at the same time, we're talking about how we need to beat China, right? And so we talked earlier in the hearing about intellectual property, balancing that with collaboration, right? How do you maintain those aspects of intellectual property that really allow us to beat China and be sustainable in defeating our adversaries when it comes to this new power source? And my question is to Dr. Reagan. How do you think we should reconcile these two concepts? And what do we do about the capital investment that will be displaced potentially pretty rapidly by a fusion breakthrough?
Yeah, thank you, Representative Begich. You know, I think you could do both. You know, we can win and beat China while at the same time deploying, first in America, a fantastic new power source that provides, with reduced externalities to traditional sources, abundant, safe, reliable power. And then we can power the world. You know, like I grew up in New Jersey. My mom and I would drive by this big steel bridge in Trenton. Says Trenton makes the world takes. That's what I want for fusion. I want it to be made here, power our grid and our manufacturing here, and then also be able to deploy it around the world. But it's an American technology we're deploying.
Dr. Mumgard, fission technology is riddled with guarded state secrets. And I'm hearing about a lot today about open and collaborative research. How much of what we're working on in the fusion space should be considered a state secret?
So fusion was declassified very early. It's because it's really hard to do, and it's also because it's not directly related to weapons. So in fusion, you don't have the chain reaction, you don't have the uranium, plutonium. It also means that you don't have what is the intent of having those things, which is when we look at a place like Iran, like you're separating out intent, energy versus weapons. Fusion doesn't have that, fundamentally, the reaction doesn't. And so that was key to why it was declassified. And that, I think, is an important principle today, that the reaction itself is universal, and the materials are universal. But the know-how is the key part. And the know-how coupled to the ability to build things is the economic engine of it. And so if we really want that economic engine to work, there's not a lot of reason to have state secrets.
China's building a new coal plant every 2 to 3 days. They're also investing in fusion, but they're not placing all their bets on fusion. Why do you think they lack the confidence to place their bets on fusion, given their investment in traditional energy?
And it's a very good question. I think it also, the answer, I think, dovetails with your previous thing about displacement of energy. The world just needs so much energy that you can't really close doors, right? If you close doors to fossil fuels in China today and you bet it all on fusion, like there's a possibility that you don't have enough energy to run that country. They're not going to do that. And what this is about building options that could expand. And every time we've built a new energy technology, it has not displaced huge amounts of energy instantaneously. It's allowed us to go faster and further by adding to it. And I think that's what the fusion story is, and that's probably how they see it.
Thanks. One more question, this one to Dr. Carter. In your experience, is there anything in recent history that indicates that China's fusion investments are motivated by a global egalitarian impulse?
I think they're very fixated on their own needs and what they're trying to spin up energy technologies and dominate them, right? I think that's the focus. I mean, we have had interaction with China over the years. They do have interactions with Europe, but I think the motivation is, as I said. Yeah.
Thank you, and I yield back to the gentleman from Arkansas.
All right. My previous friend has yielded back, and the gentleman from Florida is recognized for 5 minutes.
Thank you, Mr. Chairman. And I first want to, one of the things that a lot of us in the freshman class have been really looking at as this big AI issue comes to force is just the absolute need for energy. And I'm so glad we're having these discussions. The future is clearly at the table, and how we make these investments will be maybe if we win or lose. And it's a real challenge. And I'm glad to see that we've been listening to these type of things, making the decisions based from the experts' opinion, not a top-down situation from Congress. And I think your testimony today is absolutely vital. I'll take you from a little different tack. I chair the subcommittee on space, and it's something that a lot of people are talking about, is the idea that will helium-3 potentially move this ball forward? And a lot of people are, as always, skeptical about this, but there is a lot of potential given the reality of this being this really move from moon to here in the States and around the world to try to reduce that radioactivity that comes traditionally with nuclear energy. So the question, I'll ask Dr. Deem first, if you don't mind. Do you think this could be that innovative tool beyond what we're talking about with the issue today that could be a game changer? And do you think this technology can transfer itself in a short enough period of time to make a real impact in the energy needs we have in the future?
Thank you so much for your question. So a lot of our efforts have been traditionally focused on fusing deuterium and tritium, right? Which, as you point out, creates another challenge, which is handling with materials. But it happens at lower temperatures, so it's more readily achievable. So that's why a lot of work that we're doing has been focused on that fuel cycle. And that's, I think, the where we'll get to first. And then as you're advancing that technology and bringing fusion to market, you can also be advancing the scientific readiness of something that's based on helium-3 fuel cycle. So I think it's like a second generation to come, but it is really exciting to see with the private investments that we're actually able to dig into that deeper to make that closer to reality.
Literally, you're correct. So that idea, I think I just close with this, Mr. Chairman, because I know others want to speak, is I'm really glad that I think it's Mr. Mungard that just spoke about the idea that it's a very difficult challenge to move from traditional to these new fuels. Even when we make huge investments, we're still relying on traditional fossil fuels. And I think it's imperative that we also recognize that no matter what we do here in the States, what they're doing in India and China are polluting the rest of the world at magnitudes versus the United States. As you know, the actual carbon production in the United States has gone down over the last few years. And I've got to admit, it's incredibly frustrating as a policymaker when we see our own costs challenged because we're trying to diversify our fuel, and you see our competitors doing it at a much lower cost and impacting the world. It's not, the pollution is not just limited to China and India. And so I hope all of us policymakers will look at this as a reality that, yes, we want to make these innovative changes, but not at the expense of where we cannot be competitive around the world. And that sometimes, I think sometimes in these buildings or even in academia where I used to serve, we lose sight of the book version versus the harsh realities of a free market system, or at least a world competitive market. And so I think I've been listening to your testimony today, and I'm really grateful that hopefully we can make this breakthrough, because the last thing people want to spend money on is energy. And the thing we all are facing in these challenging times, that the AI revolution, that the only thing really holding us back, as Sam Altman talked with Congressman Begich and I and other freshmen, is the only way we're really going to maximize AI is we have the energy production to fuel this. And as we take on the challenges from China, who are using every fuel without regard for environmental concerns, despite some of their weak promises in places like the UN. So with that, Mr. Chairman, thank you very much for making the time for us. This is an important discussion, which I hope we can continue throughout this Congress. Thank you. I yield back.
Yeah, the gentleman yields back. The chair now recognizes the gentleman from Virginia for 5 minutes.
Mr. Chairman, thank you so much for allowing me to wave on. And this is my third or fourth or fifth Science Committee fusion hearing, and by far the most successful, two hydrogens and atoms hitting each other. And I just want to thank you for the progress that we've made. Dr. Mumgard, I'm very much looking forward to an invitation next year when you turn on Spark, even without tritium. Congratulations on how far you've come. Also, thank you for the announcement that you'll build perhaps the first fusion energy plant in human history in Virginia, where it belongs, rather than Arkansas or Texas. And we're excited about Helion Energy broke ground on a new thing. Dr. Regan, I never even heard of Pacific Fusion 2 years ago. So already you're here doing really great things. It's come a long, long way. Thank you also a number of times for mentioning our 4-person bipartisan 45X bill that we have in Ways and Means, which I'm very excited and I think can make really good progress. We've had a chance to meet with Secretary Wright and make sure that he is as enthusiastic as we are and that this is a bipartisan effort. One of the things I'd love for us to do is, in every speech I give, I talk about fusion, but I find that most people are still like, what's that? And not only is it what's that just in terms of the science, but in terms of what the world will look like when you are successful in the near years to come. What it will mean for, what does energy abundance actually mean? What will it mean for those of us who believe in climate change? For example, one of the things we got done in recent bills was 45Q, which allowed us to do direct air capture. But right now, if you use fossil fuels, it's a wash. But driven by fusion energy, we could make an enormous difference on the amount of carbon dioxide that's in our atmosphere. We think about it in terms of foreign policy. Most of the wars fought over the last couple of thousand years have been about energy. What happens if energy is abundant? What will this do for peace in the world? What will it do for population? What will it do for just poverty? You figure you got 2 billion people going to bed hungry every night. The scarce resource is not humanity, it's not land, it's energy. So you are ushering in a dramatic new part of human history. I'm so grateful. North Carolina talked about $40 billion over the years. I don't know where that number came from, but let's just say it's right. 10 billion, when you figure we're at 930 million in the budget that's floating around right now, and only a small fraction of that's going for things like milestones and fire. We would love to work really closely with you on exactly how that 10 billion is laid out. And go to the appropriators now, Democrat and Republican, the Rosa DeLaros and Tom Coles and the like. I did the quick math. Our overall budget's about $7 trillion. That means one out of every $700. Assuming that $10 billion is all spent in 1 year, which is probably not what you're trying to do anyway. So we're talking about one in every $2,000 dedicated to something that can make the hugest difference for mankind. There's so much that I want to talk to you about, but one, I just want to make sure that we want to work with you to define that $10 billion as best we can, knowing that it will change year to year based on our successes. On the collaboration, I know it's great with the UK and China and Japan. China's spending $6 billion. Is there any opportunity for collaboration with them? Especially when all my good friends' fears about empowering China. Already, some of the most responsible fusion companies are doing peer-reviewed articles. You're in the journals, they can read them. Is there any possibility for a productive collaboration that is not just about China stealing our IP?
Yeah, it's a really, really good question. So there is today a collaboration with China in the U.S. program through ITER. And that's an example of ITER is for everyone. And so the Chinese are getting what they need out of it. We're getting what we need out of it. And our researchers, they interact through that project. And that was really the model that we had in the last 2 decades, where we actually had a policy that we would collaborate with China. And we did learn things. They learned, I would think, more. I do think that going forward, the fundamentals of how plasmas work are so universal that, like, that is the stuff that should be in the peer-reviewed literature. The same way the fundamentals of how the human body works and how genetics work. So that's something that everyone has access to and should. The details of how do you design an actual facility, how do you manufacture it, how do you put it together, that's where the commercial interest is. That's the area that we don't collaborate on. And so I think the publication record of the companies, labs, et cetera, is following those lines, which is very similar to what's happened when we wanted to build the drug industry or when we built the aerospace industry. So I think that's healthy.
Great. Thank you. I have so much more to ask, but my time is out. So, Mr. Chairman, thank you very much.
The gentleman that criticized Texas has yielded back and has waved on for the last time. So we appreciate that. I want to thank the witnesses for their valuable testimony and the members for their questions. The record will remain open 10 days for additional comments and written questions from the members. This hearing is adjourned.